Hi friends, in our last session we have seen constant volume process and numerical based on that topic. Now in today's session we are going to see constant pressure process along with that numerical based on this process. This is Faizan Kagvi and I welcome you all to our lecture series of Basic Mechanical Engineering. So let's begin with our topic, that is constant pressure process. So it is also called as a isothermal process, and a piston cylinder arrangement for this process is already shown on your screen along with that pressure versus volume diagram, in which it is shown that this is a horizontal line, pressure is remaining constant from state 1 to state 2. So now you are very much clear that we need to do a 5 tasks. That is, first task is to determine heat transfer is how much, second task how much is the work obtained during this process, third how much is the change in internal energy during this process, next how much is the change in enthalpy delta H, and last, that is pressure, volume and temperature relationship. So let's begin with our first task. So as we know, the basic formula of heat transfer Q is equal to mc delta T. So again, for this process application is very simple. Q is equal to mcp T2 minus T1, where you have to keep in mind that Cp, as we know, is a specific heat capacity at constant pressure, m is a mass of a gas, T2 is a final temperature, T1 is the initial temperature. So this much is the amount of heat which will be transferred at constant pressure. Okay, now next we need to determine work done during this process. So we know the general formula of work done, and in this process, as you can see, heat is supplied. So displacement of a piston will take place. That is, there will be a change in volume. So the formula of work done, W is equal to P dV. Okay, now applying limits, that is integration from state 1 to state 2, P dV is equal to P V. We know integration of dV is V. Now after applying limits, the answer of work done will be P V2 minus V1. So this is the final equation for work output during this process. Okay, so 2 tasks we have completed. Our next task is to determine change in internal energy. So according to first law of thermodynamics, we know that Q is equal to delta U plus W. So from this equation, we know 2 values. First, we know heat transfer is how much. Second, we know work done is how much. So the third parameter, that is delta U, we can determine from this equation, right? So I have substituted a value of Q and W, as you can see on your screen. mcp T2 minus T1 is equal to work done is P V2 minus V1 plus delta U. Okay, now in the next step, what I have done, I have substituted a value of PV equals to mRT, that is from characteristic gas equation. So in the next step, I have written mcp T2 minus T1 is equal to mR T2 minus T1 plus delta U. Okay, so I hope that you are clear up till here. Now in the next step, what I have done, so I have substituted a value of characteristic gas constant capital R from Mayer's equation, that is R is equal to Cp minus Cv. So the next step becomes mcp T2 minus T1 is equal to mcp minus Cv into bracket T2 minus T1 plus delta U. Now making delta U as a subject, you can clearly see that the term mcp T2 minus T1 on the left side and the term on the right side, when it goes to the left side, will get cancelled out, right? So the final equation of delta U is going to become delta U is equal to mcv T2 minus T1. So this is the equation for a change in internal energy for our process, that is constant pressure process. Okay, now let's do our next task, that is to determine change in enthalpy. So it is very obvious that we know the formula we have done up till here, delta H is equal to H2 minus H1. Now the value of final enthalpy will be U2 plus PV2. So remember that when you write PV, then keep in mind that pressure is constant, so you have to mention PV2, not P2V2. Keep this in mind, otherwise the entire answer will be wrong. Okay, so next at state 1 enthalpy H1 is written U1 plus PV1. Arranging the terms, in the next step I have written U2 minus U1 plus in a bracket P V2 minus P V1. Again in this step we can write from a characteristic gas equation PV equals to mRT. So in the next step I have written CV T2 minus T1, that is our delta U, which we have determined, plus in place of PV, that is MRT. So MR in a bracket T2 minus T1. Finally, in the next step, we are substituting a value of R, that is characteristic gas constant from Mayer's equation, Cp minus Cv. So the equation becomes NCV T2 minus T1 plus N Cp minus Cv in a bracket T2 minus T1. So if you see again carefully, the term NCV and minus NCV will get cancelled out. So the final equation for delta H is going to become NCP T2 minus T1. Okay, so I hope that you are clear up till here. We have done 4 tasks, 4 parameters we have determined for constant pressure process. That is, heat is how much that is transferred during this process. Second is the work done is how much. Change in internal energy is how much. Change in enthalpy is how much. Now our last task is to determine relationship between pressure, volume and temperature. So it is very clear that, and it is very simple, that directly we are going to use combined gas equation. That is, applying it state 1 and state 2, equation is going to become T1 V1 by T1 is equal to T2 V2 by T2. Now in the next step, it is very clear that since the pressure is constant, T1 is equal to P2. So we can directly write the final equation is V1 by T1 is equal to V2 by T2. So this equation is called the pressure, volume and temperature relationship for our constant pressure process. Okay guys, so I hope that you are clear with this 5 tasks which we have performed. Now let's see numerical based on this topic. Okay. So now the question is displayed on your screen. As you can see, 5 kg of air is heated from initial volume of 0.5 meter cube to a final volume of 1.3 meter cube at constant pressure 4 bar. So in this question it is mentioned that air is heated having a mass of 5 kg and having initial volume 0.5 meter cube up to a final volume of 1.3 meter cube at a pressure P is equal to 4 bar. So what we need to do? So we need to determine first heat supplied is how much, second work done is how much, third initial and final temperature of air. We need to take Cp is equal to 1.005 kilojoule per kg Kelvin and R is equal to 0.287 kilojoule per kg Kelvin. So this is mentioned in a question. Now let's first of all write down data. So as you can see on your screen, I have written mass m is equal to 5 kg, V1 is 0.5 meter cube, V2 is 1.3 meter cube, P1 is equal to P2 is equal to P. Since the pressure is constant, so it is equal to 4 bar. Now I have converted bar into kilopascal. Okay, since R is given in kilojoules, so we need to take pressure in kilopascal. So we know 1 bar is equal to 10 raised to 5 pascal. Converting it into kilopascal, we can write 4 into 10 raised to 2 kilopascal. Okay, now we need to determine Q is how much, W is how much, T1 and T2. So let's first of all write down equations for all these parameters. So we know the equation of heat transfer at constant pressure, that is Q is equal to mCp T2 minus T1. Now see the formula carefully. What is known and what is unknown in this formula? So first of all, mass is given in a data, so it is known. Cp is also given in a data, it is known. But T2 and T1 is not given, which means that also we need to determine, right? So first, in order to find out Q, our target is to find out T1 and T2, that is initial temperature and final temperature. Now how we can determine that? So we can say that we have our formula, that is characteristic gas equation, right? That is PV is equal to MRT. Now in this equation, what is known? So we can say that pressure is constant, which is known, that is 4 bar. Initial volume V1 is also given, right? Mass is also given, that is 5 kg air. R is also given in the data, that is 0.287. So what is unknown? So we would say temperature, which can be determined from this equation. So I have substituted a value 4 into 10 raised to 2 into 0.5 is equal to 5 into 0.287 into T1. Now finally making T1 as a subject, we are getting the answer T1 is equal to 139.37 Kelvin. Okay, now T1 we have obtained. Now how we can determine T2? So we can say that we know the pressure, volume and temperature relationship, that is V1 by T1 is equal to V2 by T2.
Now we know V1, we know V2, and we have determined T1. So directly we can substitute a value and we can determine a value of T2, which is equal to 362.36 Kelvin. Now, so our first task is completed, that is to determine temperature T1 and temperature T2. Now we can directly substitute this value in an equation of heat transfer, that is Q is equal to mCp T2 minus T1. So we get the value of Q, which is equal to, as you can see on your screen, 1120.52 kilojoule. Okay, so this is one of the answer. Now our next task is to determine how much work is done during this process. So we know the formula for work transfer. What is that? So we would say W is equal to P V2 minus V1. So pressure is known, that is 4 bar. Volume V1 is how much? So we would say volume is given, that is 0.5 meter cube. V2 is also given in our data, that is 1.3 meter cube. So it's a direct application. We need to directly substitute a value and we can get a value of work done, that is W is equal to P V2 minus V1, which is equal to 4 into 10 raised to 2 in a bracket 1.3 minus 0.5, which is equal to 320 kilojoule. So this is our final answer of work output. So this is how we need to solve numerical based on this topic, constant pressure process. So I hope guys that you are clear with our topic of constant pressure process and a numerical based on this process. So we are keeping up till here in this session and we'll continue with our next process, that is our constant temperature process, in our next session. Till then, stay tuned and thank you all.